Hello everyone. In the previous videos, we have seen the concepts of measure spaces and measures, and we have gone through the basic concepts such as the Borel sets and the sigma algebra. So now let's start into the basics of probability space and probability theory. So the basic concept of probability theory is the probability space. It's a very important concept in this theory. So let's dive right into it. So a probability space is basically a probability measure such that these three conditions are satisfied. So as we had seen in our previous video, that a measure space, which is this, can be considered a measure space if for an arbitrary set omega, f is a sigma algebra on omega, and the measure mu follows these three properties as we had discussed in the last video, where measure of null set is 0, measure of countable union of disjoint sets is summation of measure of individual such disjoint sets as this, and measure of any of the set present in the sigma algebra f is non-zero. So, and also we had seen that this measure space is monotone in nature. So if you want to visit this in more detail, you can view the previous video. Now let's start with what is a probability space. So in this probability space, it is the same as that of a measure space. The only difference is that we have defined the probability measure p as this. So p of omega should be equal to 1, and this property is again derived from the measure space property. So we know that from the previously studied measure space property, if a k's are mutually exclusive, that is the a's are disjoint. So let's say a1, a2 and so on till an, and let's say this is a sigma algebra f, and such that these are all disjoint sets. So a1 intersection a2 is phi because they are disjoint. Then the measure function of a1 union a2 is measure of a1 plus measure of a2. And since probability measure is a type of measure, so it follows this property. Hence p of a1 union a2, where a1 and a2 are mutually exclusive events, is probability of a1 plus probability of a2. Okay, and similar to the measure space, probability space is also a monotone. That means there is no such thing as negative probability. So let's see the physical representation of probability space. So we had seen that, let's say this is a sample space omega. There are a few elements inside inside the sigma algebra f. Let's call them a1, a2, a3. So the probability function will map from ai, like any elements of f. So f is the domain of it, to 0, 1, which is the set of all real numbers in the closed interval of 0 to 1. To visually represent this, you can represent this on a number line. This is 0, this is 1. So let's say an element of the sigma algebra a1, p of a1 would point to some real number present between 0 and 1. So this is p of a1. Similarly, p of a2 would point to some real number between 0 and 2. We can call this p of a2. And since a1 and a2 sets are disjoint, if they are disjoint, then that means that these two events, so A1 and A2 events, are mutually exclusive. Hence, the probability of A1 plus A1 union A2, that is, if the probability of either of these two events occurring is the summation of probability of A1 plus probability of A2. Okay, and obviously since probability is a measure, so probability of the null set, which is like no event, is 0. Okay, so let's jump right into the example to understand it in a more clear way. So let's say I have a dice, and a dice can have 6 possible faces with these possible values. So this forms our sample space omega. So we can see that a dice has 6 faces and each face has one value present on it, and when you roll a dice, any one of these values can come up. So any one of the values from 1 to 6 can come up on the dice. Okay, so that would be your outcome. So the sample space is limited from 1 to 6. Now let's define a sigma algebra F such that it contains these subsets of present in the sample set omega. Okay, and let's also define the probability measure as this. So first let's verify whether the sigma algebra F is a sigma algebra or not. Okay, so the properties of sigma algebra are that it should be non-empty. So we can see F is not empty because it has 4 sets as elements. Then it should be closed under complement, which means that every element of F, and if you take the complement of any element of F, that should also be present in F. So complement of phi is omega, which is present in F. Complement of omega, which is phi, which is also present in F. Complement of 1 comma 2 is 3 4 5 6. In this case it is also present in F, and complement of 3 4 5 6 is 1 comma 2, which is also present in F. Hence this is closed under countable union. You can see our video on sigma algebra for more detail as to how to determine this, and we can also state that it is closed under countable union. Hence F is a sigma algebra on omega. Okay, so this is a valid sigma algebra. Now let's see if the probability function which we have defined P here, if it satisfies all the requirement for this to be a probability space or not. So first of all, it's a measure. So probability function, it's also a measure. So it should follow the property of measures with one extra property, that P of omega should be 1. So let's start with the probability. Let's start with seeing the conditions of the measure function mu. So first of all, P of phi should be 0, as measure of a null set is always 0. So we can see that P of phi is 0, hence this condition is satisfied. Then the next condition, let's say A1 A2 are disjoint sets. Similarly, these are all disjoint sets. Disjoint set means that A1 intersection A2 is phi. So similarly, intersection of these is empty set. So since they are disjoint, the probability of A1 union A2 till AK, all of them are disjoint, so it would be summation of P of A1 plus P of A2 plus P of AK. Let's see if this condition is satisfied or not in this example. So we can see we have two sets of disjoint sets in the sigma algebra F. We have phi and omega, and we also have this 1 2 and 3 4 5 6. Okay, so probability of phi union with omega is equal to, it's equal to 1, and this is equal to this as well, p of phi plus p of omega, as this is defined as 0 and this is defined as 1. Hence this satisfies for omega and phi. Similarly, we can try these out. So probability of 1 comma 2 union with 3 4 5 6 is nothing but this would be p of omega, which is 1, and this is also equal to p of 1 comma 2 plus p of 3 4 5 and 6, which is 0.4 plus 0.6, and this is equal to 1. Hence the probability function p is satisfying all the conditions of being a measure. Hence this is a valid measure. Now the extra property, let's see if p satisfies the extra property of p of omega being equal to 1, and we can see that p of omega is also equal to 1. Hence we can see, since f is a valid sigma algebra on omega and p is a valid measure such that p of omega is 1. Hence this omega, phi and p is a probability space. So this hence forms a probability space. So in this example, what it means is I have two events. So an individual set present in the sigma algebra function f here for a probability space can be termed as an event. So I have two events. So the probability that the dice will show either 1 or 2 is 0.4, and the probability that the dice will show 3 4, either of the three values 3 4 5 6 is 0.6. So it's not a fair dice, and the probability that it will show at any of these 6 values, obviously it has to show it, that's for sure, because a dice only has 6 faces. So this would obviously be equal to 1, and the probability that it would show no face at all is 0, because that cannot happen. It will show at least some face, some value. So in this example we have learned about how to visualize, in how to take an intuitive understanding of probability spaces. Now you can even visualize this. So for visualization, let's say you have your sample space omega here in this circle. You have 6 elements 1 2 3 4 5 6, which are 6 possible outcomes of a roll of dice. Let's say this is one of your sets in sigma algebra 1 comma 2. This is another of your sets in the sigma algebra 3 comma 4 comma 5 comma 6, and there is a mapping function p such that it maps from your sigma algebra function to this interval, which is the set of all real numbers in the closed interval of 0 to 1. So we can see here that this would be 0.4. So this would map to 0.4, and similarly p of 3 4 5 6, which is this event. So this is the event of either of these 4 values coming up on the dice. So this would be 0.6, and obviously if you take p of P of omega, which is any of these 6 values coming up on the dice, that is obviously equal to 1, and P of phi is 0. So this will give you a visual representation of probability spaces. So here the probability space is this. Omega, F and P, where F is a sigma algebra on omega. Okay, now let's take one more example. Let's say I have 4 cards and each card has a design present on it. So we have like hearts, we have spade, we have diamonds, we have clubs. So, and obviously we'll draw one of the card from these 4 cards and the probability is equal. Okay, so let's define a probability space for such an example. Okay, so your sample space omega would be this. So it's hearts, trees or clubs, diamond and spade. Okay, and let's define a sigma algebra such as this. So I am defining a sigma algebra in which I am defining the null space phi, and I am defining omega. I am defining the red color design. So this is red color design. So it would contain hearts and diamonds. So this subset would contain hearts and diamonds as they are red. I am also defining another subset called black color design, which would contain spade and club. Okay, so let's first verify whether F is a sigma algebra or not. So we can see that F is non-empty as it has 4 subsets present, so it's not empty. Is it closed under complement? Yes, it is closed under complement, as the complement of this omega would be phi, the complement of phi would be omega, complement of red cards would be black cards, the complement of black cards would be red cards. So we can see that in this sigma algebra F, we have basically defined 4 types of events. The first event is that any of the card can come up, like red, spade, diamond or club. Okay, and we have a null set, which is an event that none of the card comes up, which is an impossible event. And we have one more event such that a red card comes up, and we have another event which means the black card comes up, either spade or club. So we have these 4 types of events which are possible in our experiment. Okay, so and also we can see that F is closed under countable union. So hence F is a sigma algebra on omega. Okay, since F is a valid sigma algebra, we can again continue. Now this is a fair experiment, so the probability of turning a card is equal for all. But since we don't know what is the probability of, let's say, getting a heart, because it's not defined, the heart is not present as a set, it is not present in the sigma algebra, so we cannot just directly define it as 0.25, which would be incorrect. So for this we are kind of limited by our sigma algebra F. So we can see first of all by the property, the P of phi would obviously be 0, because this is a measure, so it will follow the properties of measure, and measure of phi is 0. P of omega is 1, because this follows the property of probability measure. So since this is a probability measure, the probability measure of omega is always 1. Now the probability of hearts or diamonds is half, since it's a fair experiment. So the cards are fair, let's say. And similarly, the probability of getting a spade and a club is also half. Now we can see that the probability measure P satisfies all the condition of being a probability measure. Hence, we can see that in this example, where the sample space is these four types of symbols of card, the sigma algebra F is defined as this, where we have like phi, omega, black cards, and the set of red cards, and the probability measure defined as these four, where p of phi is 0, p of omega is 1 by the property, and the probability of getting a red card is half, probability of getting a black card is half. This follows all the properties of a probability measure. Hence, this above example, omega, f, and p form a probability space. Hope this example makes this concept easier to identify. We can also see this visually, that let's say this is an event, heart and diamond. So the event that the event that the card drawn is either of these two is a part of sigma algebra, yes. So the probability of getting a heart or a diamond is half, so it points to half. Similarly, the probability of getting a black card is also half. And this also follows that probability of union of disjoint sets is summation of the probability of those disjoint sets. So these events are mutually exclusive. So you can see either you can get a red card like this, or you can get a black card like this. So these two events are mutually exclusive. Either you can get a red card or you can get a black card when you draw a card. And this obviously follows that this happened because these two sets are disjoint. So the intersection of these two sets is phi. So these two sets are disjoint. Hence, these two events are mutually exclusive. So either you can get a red card or you can get a black card. And so the probability of union of this should be equal to the individual probability of getting a red card or a black card. Okay, and we can see that this is nothing but p of omega, and this is 1, and this individual sum of the properties was half plus half, so this is also equal to 1, and this follows the probability property that the sum of mutually exclusive events, so the union of all the mutually exclusive events is the sum of individual probabilities. So this is a valid probability space, and I hope this example clears everything, and let's see you in another video. Thank you for watching.